Now, let's talk about how to evaluate inductances. Of course, whenever you receive a problem, first thing, the most important thing is you have to choose a good orthogonal coordinate system to work with, okay? Depending on your problem geometry. So always define your coordinate system, and then you assume you send in an operational current. Okay, you have to assume you have a steady state current to give rise to magnetic field lines. Okay, so you assume a current value, then you calculate B. You have multiple ways to calculate B. We can use Ampere's circuital law, or you can use Biot-Savart law. Okay, it's your choice. This is Ampere's circuital law. This is Biot-Savart. But if you use this one, you have to have a good understanding to the problem. And usually you have to have good symmetries. If your problem is not really symmetric and you don't have good insights, just use brute force, Biot-Savart. But whenever you use Biot-Savart, it's a test to your ability to perform vector analysis, vector calculus, okay? But in any case, once you have B, you calculate the flux linkage. Once you have B, you perform the surface integration to get the flux and multiply by the number of winding to get the flux linkage. Once you have the flux linkage, you divide by the operational current to obtain the flux. Okay? So the procedure is very clear. You have to assume a current. You get B, you perform surface integration and multiply by the number of turns to get the flux linkage, and then you divide by I. So a big question to you now. Whenever you are asked to perform or to calculate the inductance, after all your hard works, your answer, should your answer, your L value, should it be dependent of the operational current? Cannot be, okay? So the first thing to check is for your L value, there should be no I in it, okay? Remember, if you don't believe me, some of you will make this mistake. You turn in your examination answer, but there is L is I dependent. You know you're wrong, okay? As we talked about, L is only depending on the geometry and the material. It does not depend on your operational current. Therefore, in your result, there cannot be I, okay? Okay, so let's take a look at this problem. This is a solenoid that we analyzed before. Same thing, but now we can calculate its self-inductance, right? I don't have to go over again. For this solenoid, we generate field lines only inside, okay? Nothing outside, because we have assumed this is extremely long, okay? So basically, the B flux density is pointing in the negative Z direction because the current is now flowing this way, right? So your thumb is pointing to the left. And the value is mu0 and I. N is the number of winding per unit length, okay? Mu0 means inside it, even though this is colored for you, but actually this solenoid is hollow. There's nothing inside. You only have the coil. You have nothing inside, so you have free space. Or you have a non-magnetic material, okay? You already see the material response here. Mu zero means it's treated as vacuum. But if you have a magnetic core stuck inside, all you have to do is change or multiply by mu r. Okay? You already see the material response. 5. Once we have B, we need to calculate the flux linkage. Before you calculate the flux linkage, it's safer for you to calculate the flux. Flux is, in this case, B is a constant inside. So the surface integration is direct multiplication of the surface area, right? Pi b squared. What is B? B is the radius of the circle. Okay? So you see material response and geometrical response already. If the geometry is not circular, you don't expect to see pi b squared. Okay? Now that we have the flux, what about the flux linkage? Well, the flux linkage is your flux multiplied by the number of total winding. But in this case, because we have assumed the length is infinite, and the question is asking the inductance per unit length. So we need to multiply by the winding density. Total n terms divided by a total length of L, and that is non-capitalized n, right? The winding density. All right. We finally have the flux linkage. We should divide by I. That's your self-inductance per unit length. Okay? First thing to check is your answer I-dependent? Luckily, there is no current. Okay? So you know you are 50% or 70% right because your answer is not depending on the current. Okay? Second question you should ask, do you see any material sensitivity? Yes, you do, mu zero, meaning here the core is non-magnetic. So if you were to change the core material, you don't have to repeat your calculation again. All you have to do is change the relative permeability. Okay? So material response is checked. Geometric response, pi b squared. This is the geometric response. Everything checked. First, there's no current dependence. Second, you see obvious, evident material dependence. Third, you see evident geometric dependence. Okay? You always need to do this self-consistency check. All right, such a simple problem. What can we learn from it? Well, we learned how to calculate self-inductance. But as a future engineer or scientist, think hard. If, again, this is your first job, your first task, if you don't get it, you'll be fired. This is your first day of work. Your boss wants to make a huge inductance, but in a very cost-effective way. How would you approach this problem? So you're entering type power for the first day, right? After all the training, all the hard works, you graduated. You expect to earn 40, 50,000 per month. And this is your first problem. You want to create a huge L prime value, but without spending too much money. How would you do it? Any thoughts? What I'm trying to illustrate Well, first check is there is no current dependence, right? Then the engineering aspect tells you you have the freedom to change the L prime value. First thing is you see obvious material response, mu 0, okay? So is there anyone proposing to increase L prime by increasing mu from mu 0 to some mu value? Anyone? Raise your hand. Don't be shy. I mean, this is not having a definite answer. No hands. So you're all fired. No hands means you're fired. You don't know how to do. Is that real? Geometric response, pi b squared. Increase the radius. Right? When you increase the radius, you have a square dependence. It's easier than this one, right? Well, if you use a magnetic core, so maybe the relative permeability is 100, but here you increase your radius by a factor of 10. You get 100 times bigger. So this is more efficient, actually. What else? What else? You all know the answer, so why aren't you talking? You know that I'm not pointing to the right direction, so now finally, I'm pointing to this one, and everybody nodding your head. So Taiwanese student, Asian student never speak, but they all know what they're doing. That's impressive. So as you can see, this is also geometric response, actually, right? N is the number of windings. So you don't really have to increase your geometry. Maybe you want to fit this coil into a very small closure, so you're not allowed to make it bigger, but why not just make the winding number larger, and you also have the square response, okay? So if I were you, I would evaluate at the same time. If the limitation is the device size cannot be changed, I cannot change B, but I can at the same time increase the winding number, and also by replacing a magnetic core into the coil, right? So maybe this is increased by 100 times, this is another 100 times, you have 10,000? Yeah, 10,000. Right? Okay. So hopefully everybody passed your test and can stay in your first job. What I'm trying to say is geometric and material responses are your tuning parameters, and that's where engineering comes in play. Okay? Otherwise, you're only studying this in a mathematical way, mathematical sense. You have to tie to your daily life analogy, okay? Second case, similar. Do I really need to go over? Just study on your own, okay? Basically the same. Finally, let's talk about energy, okay? Energy. If we have an operational loop, you have to respect it in a way it is storing energy in the form of magnetism, okay? So we're going to talk about the energy of a current loop, and we also want to formulate the energy stored in magnetic fields, all right? So let's come back to the first loop. We look at it, it's already operational with a constant current value of I1. But somehow, as we talked about, current does not come in for free. It is operating at I1 because for a certain time duration, we slowly increased the current value from 0 to I1. Okay? And starting from this moment and onwards, the current is kept as a constant. But there is a time of transition, okay, where you have gradually changing of current value. So now the bigger question is, how do we calculate the energy being stored in this single loop? This is a test to your understanding and to your memory of what you learned in electric circuits. If you have a time varying current over a loop, right? Now you understand the loop is actually an inductor. So if you know the inductance of this loop, and you know how the current flowing across it is changing as a function of time, what do you know? You know the voltage as a function of time, right? Well, or maybe not a function of time, okay? But once you have a time varying current and you know its inductance value, you know the voltage, okay? We call electromotive force, right? So what we're assuming now is initially at time equals to 0, there's no current, but over a certain period of time, the current is increased from 0 to I1 gradually. Then we can calculate work, right? We're working to set up the current to its operational current value of I1. So that work will be the energy stored inside the loop. Okay? And work is VI, right? V times I is power. Power performing an integration over time gives you energy or work, right? All we have to evaluate is V times I and integrate over the entire duration. So V, we already know. I is something we supplied. Okay? So everything is known. Okay, tell me this. You're falling asleep. Have you seen this relationship before? The energy stored in an inductor is 1/2 L times I squared. You saw this, right? Okay? So there's nothing new. And from the definition of L, inductance is flux linkage divided by I. You can write it in another form. Okay? So whenever you have an operational current loop, you are storing energy, right? And you have to know its inductance. Okay? So the question now is bigger. Well, what happens if I have the second loop? How much energy is being stored in this entire system? So the procedure is, well, we gradually increased the operational current of loop number 1 from 0 to I1. Okay? Once it reaches I1, we keep the current value a constant. We continuously supply its current value to be I1. And then we know the energy being stored in such loop is 1/2 Li squared. But then now, we insert the second loop into its position. Okay? Once loop number 2 is in its position, we do the same thing. We also increase its operational current from 0 to I2. Okay? From 0 to I2, also slowly. In this case, when the second loop is also operating, it generates field lines of its own. But once loop number 2 is operating and having its own magnetic field lines, some of the field lines would also cross the surface area of the first loop. And that's called mutual inductance, right? So in this case, well, when the current over loop number 2 is gradually changing, this loop is also developing some electromotive force, right? But the electromotive force is now applied over loop number 1 through mutual inductance. Okay? So how do we evaluate the energy that is stored in this system due to mutual inductance? Again, V times I. But now you have to be very careful. W21 means to the first subscript, loop number 2 is responsible for generating the field lines. And loop number 1 is the one receiving this free field lines. Okay? So therefore, I is the operational current over the first loop. But the voltage is the one created by loop number 2 and impressed over loop number 1. Okay? So due to the presence of mutual inductance, or these two loops are coupled in some sense, you have to work additionally to get it right. Okay? Because you have mutual inductance. This is the additional amount of work that you need to keep these two loops operating. In the end, you want loop number 1 to operate at I1 and loop number 2 to operate at I2. But is that all? The total amount of energy stored in this two loop is basically W1 plus W21. Is that it? Don't ever forget, in the process of making this operational, you also need the third fraction of energy to keep it moving, right? So that is 1/2 L2I2 squared. So in the end, you have to add all these three components up. That is the total work. Okay? So the total work is having three portions. You can view this, due to the mutual inductance, as two portions of 1/2 L21 I1 I2 and multiply by 2. Okay? So what I'm proposing now is we write it in this more fancy way of writing, so your younger sisters or brothers would admire you, right? Writing this is not big deal, but writing this double summation, oh, you're very good. You have improved. So professors like to write this mathematical form, so you would admire me. But I'm not that type of professor, okay? I'm very humble, okay? So time is pretty much up for this class, but we have another 15 minutes, so we can go into more details. The very reason for writing out the total work in this form is, well, now we only analyze two loops. But in the real world, we might have 100 loops, right? So double summation is really helping you. If you understand the meaning of the double summation, then you can have a generalized relationship. And eventually, we want to start from the generalized relationship, and we want to have a form to describe the energy stored in fields rather in loops. Now we're only talking about the loops, okay? We have to know how many loops we have. But in the end, we only care how many field lines we have in space, okay? So that's for the next class. Question up to now.